Okay, let's start. So, hello everyone, and thank you for assisting to this very exciting talk. We are privileged today to have with us Dr. Alhussein Fawzi, who is a remarkable researcher working at the forefront of artificial intelligence and computational discovery. So, before letting him start his talk, I will introduce him very briefly. So, Dr. Al-Hussein is the co-founder and CEO of a stealth startup, and until very recently, he was a research scientist at Google DeepMind. In 2023, he was awarded the MIT Innovators Under 35 award for his innovative use of machine learning to push the boundaries of computational science and algorithm design. He worked extensively on AI for science, with a specific focus on how machine learning can unlock new mathematical and computational results. He has published over 30 papers in leading journals and conferences, including notably 2 papers in Nature 2022 and 2023, showcasing how AI and large language models can be applied to discover new algorithms for fundamental tasks such as matrix multiplication and sorting, and even uncover new mathematical insights. So, with no further ado, Dr. Al-Hussein, the stage is yours.
Thank you very much, Ziad. It's a great pleasure to be here. Let me share my screen. Yeah, I mean, I guess you can see my screen now.
Yes.
Yeah, okay.
Mm-hmm.
Yeah, it's a great honor and pleasure to be here. I'd like to talk to you today about how we can use essentially foundation models in order to make new discoveries, right? So if you think of foundation models and large language models in particular as a compression of the whole human knowledge, right? So these models have been trained on the whole of internet. How can we use those models in order to discover new stuff, essentially, new stuff, especially in the algorithmic space, right? So how can we discover new algorithms, right? So before I go into the details of how we can do that, the method and so on, I'd like to tell you a little bit of why this is important. Why do we need to discover new algorithms today? Now, if you look at the kind of decision-making problems that we are faced with today, these have been increasing in complexity significantly in the past few years, exponentially even. By complexity, I mean the scale and the fact that these problems are becoming very much dynamic, right? So if you look, for example, at the data center space, right? So data centers are expected to essentially consume more energy than in Japan, than the country of Japan by 2026. This tells you how much these data centers are energy consuming, and that there is a significant need to kind of tackle this problem of energy consumption of data centers, right? So if you think about what are the main causes of energy consumption in data centers, that's, for example, cooling, but also many other factors. So how do you essentially tackle those problems is really a fundamental and topical challenge that we are faced with today. But that's not only that's not the only, of course, domain that where decision making is really becoming fundamental. Plant optimization. You have a bunch of like power plants, and you'd like to determine how much electricity to generate from each power plant in such a way to meet the loads and satisfy the physical constraints, the engineering constraints, and so on. Again, the scale of things with renewables now is becoming much much bigger than what we were used to. Another domain is that of scientific discovery, right? So as we have more and more robot scientists today that are doing the experiments by themselves, how do I, like the decision-making problem that I need to face at each step here is, what experiment do I need to do in order to maximize my chance of getting a certain discovery at the end, right? So let's say I want to discover new material or something like that. What is the hypothesis that I need to do at each step in order to maximize my chance of actually getting this discovery at the very end? Right, so all these are very difficult decision-making problems that have increased significantly in scale, and that are really like need to be solved in real time. So my argument that one of the, or maybe the thing I'd like to maybe communicate is that one of the fundamental bottlenecks that we do have today is algorithmic. If you actually look at how these decision-making problems that I was talking about in the previous slide are solved, you'd be surprised by the fact that most solutions are based on static, decades-old heuristics, right? So these are like to solve these decision-making problems, the ones in data centers or plant optimization and so on. Usually they do involve essentially heuristics that have been invented decades ago and that are essentially, sitting in books, right? And that are static and that do not adapt to the specific use case that you are dealing with, right? So this is really fundamentally flawed because of the scale of the decision-making problems that we are faced with, and the kind of new challenges that we're faced with. Now, of course, there are some machine learning methods to tackle those problems. Now, the problem with these machine learning methods, however, is that they are based on neural networks. They are based, for example, on deploying a neural network, and so they are not really trustworthy in the sense that you cannot really trust a neural network to control your data center, for example. What if it hallucinates? What if it does, something that is out of distribution and so on? It does not really work well with hard constraints, are hard and expensive to deploy, and so on and so forth. So what I'd like to tell you today is essentially another way, a new paradigm to design new algorithms, which is essentially in the space of code. So we will be designing new algorithms in the space of code, but we will be using foundation models to do that. Great. Okay, so kind of to summarize a little bit what my mission is and what my mission has been in the past years is essentially to discover new, verifiably correct and efficient algorithms for impactful problems using machine learning. So there is a few keywords here. Verifiably correct algorithms, meaning that I want to design algorithms that are trustworthy, right? That can also be verified, that are interpretable. I should have added here interpretable. I want to do this for impactful problems, what I call root node problems, in such a way that if you solve this problem, if you design new algorithms for that problem, then it has so many implications down the line, right? So one of the first projects I worked on in this space is that of matrix multiplication, and I'm sure most of you are familiar with the problem of matrix multiplication, but if you're not, that's essentially an operation that's really at the core of all modern computation, whether that's training neural networks, whether that's simulation and so on and so forth. Matrix multiplication is really heavily used for all these fundamental problems. And so the question that we were asking is, okay, matrix multiplication is that fundamental root node problem. Can we use AI and machine learning in order to discover new algorithms that are faster than we know so far, but that are still verifiably correct and it doesn't hallucinate and so on? Just maybe to give you a quick, really, I mean, this talk is not meant to be really technical, but just maybe to give you some flavor of the kind of things that we were doing. So this is the operation of matrix multiplication, right? So 2x2 matrix multiplication. I'm sure most of you are familiar with this operation. So that's essentially the standard way of doing matrix multiplication, 2x2 matrix multiplication that we are taught in university or high school, right? So this was thought to be the best algorithm to do matrix multiplication. Now, there is a German mathematician that came in 1969 and said, actually, I have a better way of doing matrix multiplication. How is that? Well, you do these operations here on the right? So you combine the entries of A together, you combine the entry of B together in a very weird way, I have to say, right? So this is very non-intuitive for humans, right? And then you combine these entries in a way that is shown here. And now, if you actually do the expansion, right, of this expression, then you will get exactly the operation of matrix multiplication that you have on the left here, right? So you'll have cancellations, and the operation that you'll get on the right here corresponds exactly to matrix multiplication. Very hard to find for a human, but once someone gives you this algorithm, it's actually easy for you to check that it's correct, right? And so this was a mathematician, a human mathematician, that was able to come up with this. And why is this better than the traditional operation of traditional way of doing matrix multiplication? Well, that's because here you involve only 7 scalar multiplication as opposed to 8 here, right? So the standard algorithm for doing matrix multiplication involves 8 multiplications, right? And so if you do this in blocks, right? So you don't do, I mean, this is not only an algorithm to do matrix multiplication on 2 by 2 matrices. You can use this on n by n matrices, but you decompose them into blocks. Then you get an algorithm to do matrix multiplication that is much faster than the traditional way of doing matrix multiplication, which is n to the power log base 2 of 7, which is better than n cubed, right? Now, why do I show you this slide? Because like the first time I saw this algorithm here, this is, I think, an indication of the fact that, look, I mean, AI and machine learning should be much better at finding those algorithms than us, right? This is really hard to find an intuition of actually how do you determine this algorithm, right? And this is exactly what we did in this paper here. Now, we formulated the problem of designing new algorithms to do matrix multiplication as a game, as a single player game. But this game turns out to be much, much harder than things, for example, like Go, right? Go as a fundamental challenge, like a fundamental AI challenge that was essentially long-standing for decades. And AlphaGo was able to essentially solve this challenge, but this was considered to be a significantly hard problem. Well, consider this problem as much, much harder in terms of numbers, in terms of the action space is really, really large. What do I mean by action space is that at each step, what you need to, like the number of possibilities that you need to choose from are way, way bigger than the number of possibilities that you need to choose from in Go, right? So in Go, the number of possibilities you need to choose from at each step is essentially the board size, right? So 19 by 19. Here, in order to design new algorithms to do matrix multiplication, well, that's essentially a very, very big number as shown in this row here. So what did this project involve? Right? So what did this project involve? It was a multi-year project in order to design new algorithms to do matrix multiplication. But I want to tell you a little bit about like the components of this project. The first part was essentially to model this problem, right? So, I mean, designing new algorithms to do matrix multiplication doesn't seem like a game, right? Well, converting this into a game was a significant, step, right? As a combinatorial game where you have a sequential process, right? At each, you have a board, the 3D board, the tensor, and then at each step you can choose from a set of actions, and then you repeat essentially sequentially until you get a final reward, and then you win or you lose, right? So you can, I won't go into the details of how you actually convert this into a game, but there is a significant step in the modeling aspect of things. Then there is building the method itself, right? So this involves essentially building a policy network, a value network, incorporating some of the asymmetries in the problem, right? And then having a distributed system to solve this problem. And then essentially running this, right? Running this on a distributed setup, right? And then running this for a few days, and then at the end getting your, after a lot of experimentation, of course, getting the new algorithms to do matrix multiplication. And what I'm showing here is indeed a new algorithm that was improved over Strassen's algorithm for the first time for many years, right? So these are the different steps essentially that were needed in order to make this new discovery, right? Now, the question I want to ask is, okay, I mean, this was really good in order to design new algorithms to do matrix multiplication, but then like, if you really want to apply this to another problem, right? So say some of the problems that I was talking about in the first slide, right? The problem in the energy space, for example, and so on. Algorithmic problem in the energy space. Do I need to really go through this multi-year effort to design an agent for a single problem? That is really a challenge, right? So we don't want to kind of like spend 2 years on each problem. It requires a significant amount of resources, right? So reinforcement learning is really heavy in terms of resources. And then many problems do not lend themselves to this nice game approach, that nice game and combinatorial approach, right? So there are some challenges with this high-level approach that we use in order to design new algorithms to do matrix multiplication. And what I would like to tell you in the rest of my talk is essentially how to leverage foundation models for discovering new algorithms surpassing state of the art. Instead of doing something that's super specific to one particular problem, like for example, matrix multiplication, I want to tell you more about like, okay, designing something more high level that's able to solve many problems. Okay, so the first idea that we can think of is essentially to use foundation models to do what we did with matrix multiplication, to say, okay, can you like ask ChatGPT essentially, can you design a fast algorithm to do matrix multiplication? Can you discover a new algorithm to do matrix multiplication faster than Strassen's algorithm, right? That's the first way we can think of things, right? Now, of course, what you'll get is either of two things, you know. You'll either get some sort of like result from Stack Overflow or something like existing result, which is really not what we want. We want to really discover new algorithms to do matrix multiplication or faster than what's existing already. But most likely what you'll actually be getting is some hallucination, right? So you'll be getting an algorithm or like something that doesn't make sense at all, like what's shown on the left, right here. So that's not interesting. Now, does it mean that language models and foundation models are not useful at all for this exercise? No, they're actually really useful, but you have to use them in the right way, right? So what our approach consists of, which is called fun search, as an insertion in the function space, is to combine the creativity of large language models with the guardrails and verification of an evaluator, right? So many problems in computer science and in mathematics have this property that evaluating them is easy, but solving is really hard, right? So if you give me a candidate solution from the traveling salesman problem, for example, it's easy for me to check whether this is a valid solution or no and score it, right? Similarly, if you give me a candidate tensor decomposition, it's easy for me to check that this is really a tensor decomposition, independent set, and so on. So many problems fall under this category of that evaluating them, like given a candidate solution, it's easy for me to check that it's a real solution and score it. But getting to a solution is hard. Like finding a good tour for the traveling salesman problem is really a difficult task, right? So our approach is to essentially focus on this kind of problems where evaluating is possible, but solving is hard. And fun search, as in search in the function space, what we'll do is to search in the function space using large language models in order to go from this evaluate function, which your assumer is given, to a solve function, okay? So this evaluate, remember, is a function that takes as input a candidate solution and then scores it, tells you how good it is, right? And we assume that we are given this function here. So at the high level, how does this work? How does this essentially like fun search and search in the function space work? So think of the function space here as a 2D space for kind of like pictorial representation, where you have colors, right? Each point is a function, right? And the blue color indicates functions that score low in terms of the evaluate function. And the red color here is functions that score high in terms of the evaluate function, right? So I'm starting here from a sole function that is in the blue region, right? That doesn't score well. And my goal is really to kind of like hill climb and go and be able to go towards functions that score high on the left-hand side here, right? Of course, like this is a simplification. Like the space of possible functions is huge, right? I'm just representing here in 2D so that we can try to understand what we're doing and what's happening. So if you sample, so we want to start from this solve v0 that is a trivial kind of algorithm. We're going to then sample from the LLM, ask the LLM to improve over this solve v0, right? Now, in maybe 90% of the cases, what you'll be getting is either functions that don't, like run, or functions that don't improve in terms of score and so on. But in some cases, you'll actually be getting some interesting ideas, right? Some interesting ideas that potentially improve over the initial score of solve v0. But still, it's very unlikely to reach the left-hand side here, right? So instead, what we'll be doing, and that's the high level, is to chain the mutations together in order to arrive to this region that is on the left. So think of this as essentially doing an evolutionary algorithm on top of large language models. The mutations are provided by the large language model, and then we have an evolutionary process, an evolutionary algorithm that's able to select which mutation to do I want to build on top, and then kind of like compose those mutations together until you reach the thing on the left here, okay? So a bit more specifically, the input to this method fun search is a specification, which is an evaluate function and a first a solve v0, right? An initial solve function. I'm going to initialize my population or my programs database with this solve v0. Then I'm going to select a few items from the prompt, a few items from this population or from this programs database, which I'm going to put in the prompt. Now, of course, the most important thing in this whole algorithm is how do I select these programs, right? That's the kind of like the whole intelligence is in how do you select the right the programs that are the most promising. Okay, but I won't go into the details of that because it's quite technical, but let's assume that we have a way to essentially like select some programs from the programs database. I'm going to put this in the prompt and I'm going to ask the large language model, can you improve over these programs that I selected in my programs database, okay? Now, as I said, if you run this through the evaluate function, most of the programs are not going to run or maybe some have some sort of error. I'm going to take the ones that do actually run and then add them back to the programs database, right? So that it's able to build on top of them in a later round, right? And then later on, I'm going to essentially so I'm going to run this iteratively. And then at the very end, I'm going to get this novel program that is essentially solving my problem. So at a high level, quite easy, really. Think of this really as an evolutionary or genetic programming, but we're using large language models in order to help us with the mutations. Okay, let me go let me show you some results of how can this actually like apply or how the kind of results that we get on hard problems. So the first problem that we applied this to is the maximum independent set problem. So the maximum independent set problem is you have a graph and you'd like to determine what is the largest number of nodes in this graph in such a way that no two nodes are connected, right? So that's a really hard problem. It's an NP-hard problem. Now, we don't just want to solve this maximum independent set problem for all possible graphs, but rather we want to focus on graphs or distribution of graphs that have particular mathematical significance. So we focused on one distribution to the extent that someone like one of the most famous or perhaps the most famous mathematician says that this is his favorite open question, and that's called the cap set graph, right? So if we apply this fun search approach on this distribution of graphs, so for small graphs, what we're able to get is essentially the same as the state of the art, right? So here, the previous best construction for n is equal to 2 was 4, right? So a subset of size 4. And then for 3, we match also the state of the art. 4, we match state of the art, and so on. But then the idea is that when we go to very, very large graphs, then this is where this method shines. Because remember when I was telling you about the scale of problems that is increasing significantly now, and this is where human intuition really fails, this is the kind of regime where this methodology works really well, where we don't have intuition anymore for these very large graphs, and therefore this kind of methodology works well. And this is precisely what we see here, is that for very large graphs, we are able to surpass state of the art with this approach, right? So we use a large language model in a loop like that, and we're able to find functions that generate independent sets that are larger than what we know so far. We also did this asymptotically, so even it's able to generate cap sets that are larger than what we know asymptotically. Now, one very important point here beyond the actual quantitative results is the nature of outputs that we're getting. Now, if you have a search, a traditional search procedure, what you'll be getting when you apply this to the independent set problem is a list of nodes, right? A list of 512 nodes, right? And then, you know, like you don't understand anything from it, right? Look at it and okay, you can see it, but it's really hard to know what's the underlying mechanism that allowed to generate this large independent set. Here, what we are searching for is a program, right? So we are searching for a program in the space of functions, right? And when we execute this program, then we get this this large independent set, this solution that we have on the left here. So, of course, you know, like if you're a mathematician and you look at the left, you don't understand anything of like how did this get generated. But looking at the right, you're actually looking at the code that allow you to generate this thing on the left. So it's much more interpretable from a human point of view, from a domain expertise point of view, and this is really fundamental. So we actually worked with a mathematician who was able to look at the code that was generated by this fund search, which is on the left here, what he's saying is that when he studies this kind of programs, he's actually learning something from them, right? So up to our knowledge, this is the first time a scientific discovery was actually made using a large language model or with the help of large language models. So it's a provably new piece of verifiably true knowledge about a relevant scientific problem, but it's also a new computational paradigm because it's a new way to discover understanding rather than just facts. So a fact is just a bunch of numbers that you don't understand anything from. But understanding is really what is the program that allow you to generate this this bunch of numbers. Okay. Now I just want to say, yeah, maybe one thing that is maybe for the people who like technical stuff. We have thought a lot about why does this thing work, right? Because it's quite surprising that it actually works at all. So I have a hypothesis why it works. Is that because most problems that we care about are highly structured, the solutions tend to have a small Kolmogorov complexity. So maybe just what is the Kolmogorov complexity of y? It's the length of the shortest computer program that outputs y. So for example, the Kolmogorov complexity of the string AB is much lower than the Kolmogorov complexity of a random string, right? Because there is a program, a short program to generate the string AB, right? So fund search's implicit prior is encouraging solutions that have a small Kolmogorov complexity, right? And so it makes the search space much better. So searching in the program space becomes much more efficient than searching in the space of solutions directly, or searching in the space of numbers directly, right? And this is, I think, why, or one reason why this approach of searching in the function space is much better than searching in the space of solutions itself. I have a few minutes left, so let me tell you a little bit about like how can you use this for practical purposes also, because so far I've been talking about math, but this actually, that's really the beauty of it, is that you can apply it on many different problems. So we tried this on online bin packing problem, right? So online bin packing problem is a problem that is really present everywhere, from, you know, like packing items into, or containers into ships, to, you know, like scheduling jobs into data centers. That's essentially the same problem that is being used across many different domains. So what is the problem? The problem is that if you're given a fixed collection of bins and a stream of incoming items, and you'd like to place each item to minimize the total number of bins used. Okay, so yeah, so for example, this is an illustration of items that are incoming into bins, right? And your role is to essentially determine which bin to place, sorry, which item to place on which bin, right? And here on the left, what we have is like an existing heuristic, and what we have on the right here is the heuristic that was found using fund search. You can see that the fund search heuristics uses less bins, uses one less bin than the best fit heuristic that you have on the left here. Okay, but that's, of course, that's a toy example. If you actually apply this in practice, what you're getting is significant improvements compared to existing heuristics, right? And it uses, what this means is that it uses much like less bins compared to existing heuristics, right? So you can pack your items in less bins compared to existing heuristics. Again, I think one important thing to note here is that is this contrast between solving this problem using neural networks, in which case you'd need to actually deploy a neural network. Let's say you want to solve this problem using machine learning. So in that case, what you need is to deploy a neural network to solve your problem, which is really problematic because you're not able to read what's in a neural network. What if like it hallucinates at some point? What should I do? Here, what you're doing is that you're using large language models and this evolutionary process in order to find a function to solve your problem, right? So you're able then to read it. So the domain expert is able to read this function, edit it if needed, like add things, add if conditions if needed, and so on, and then deploy it, right? So from a deployability point of view, from a debugging point of view, from an understandability point of view, predictable and also much more scalable. So this has really lots of benefits when it comes to deploying this stuff in the real world. So for which kind of problems does this approach works well? Well, it works particularly well when you have an efficient evaluator that's available. As I said, of course, you also need to have a smooth scoring feedback, not a binary decision, right? So 0 or 1, so that it's possible to do this hill climbing and possible to gradually improve the solution. So if you're interested, take a look at the paper in Nature that describes all this, mathematical discoveries from program search with the large language models. Now, beyond what I described, I'm really convinced that this is really we are witnessing the birth of LLM discovered algorithms, right? As I said, we are at the forefront now of decision-making problems that are increasing in scale, that are increasing in complexity, and so on. And we really need those kind of LLM discovered algorithms that go beyond human intuition in order to solve those in a way that's interpretable, that's verifiably correct and data-driven. And that's precisely what I'm really focusing on. That's the end of my talk. Thank you very much. If you have any questions, please let me know or drop me an email. Thank you.
Thank you very much, Dr. Hussein. It was a very interesting talk. Personally, I knew a little bit about algorithm discovery using AI, but I never went in depth into this field. And your talk was very interesting. So if you still have some time, we may have some questions from the audience.
Okay.
So the first question is from Ashraf. He is asking if the LLM used fine-tuned on instances on your problem, or is it just a foundation model pre-trained on some generic tests on the internet?
No, so it's not fine-tuning anyway. Actually, there is no training. There is no gradient propagation at all in what I discussed. So there is no training essentially. So the LLM that we used is a traditional LLM. It has to be, of course, trained on code, significantly trained on code, but that's about it, right? So so it's not fine-tuned on any sort of like problem like the cap set, for example. That's not the case at all. So it's a generic LLM. Now, of course, one might improve the results if you fine-tune on specific problems and so on. But what we want to highlight here is that even with an LLM that is like off the shelf, you're essentially able to get those results.
Mm-hmm. Sorry, Professor Fawzi, if you can just stop sharing your screen, maybe it will be just to be more visible for the audience.
Okay.
So, and please, I also have a question. So in the problems you described, what I understood is the process generally works like this. You use the LLMs first to find an algorithm, but then you need some human feedback to prove that the algorithm is correct and to prove its complexity. Do you think that this is something that can be also automated somehow?
Yeah, definitely. That's a great question. So definitely there is, I think, a lot of work in this direction of automating the verification side of things too. Now, in many cases, when you actually try to discover new algorithms, you can let the LLM only play in a part of the space that makes sure that the whole algorithm will be correct. Right. So, for example, if you think about greedy algorithms, then you essentially don't give the LLM an empty sheet of paper and you tell it, okay, like do whatever you want. No, you actually, what we saw is that the best approach is to give it what we call a skeleton. So a skeleton of a greedy algorithm, and then you only let it do the things that we as humans are not able to do, which is, for example, what is the order at which I should visit my elements, right? In a greedy algorithm, right? And so in this case, it doesn't matter what order it's going to visit the elements, it's going to be correct at the very end.
Okay.
But yeah, giving it a skeleton to make sure that it's correct, and then let it do the things that as us we don't know how to do. This is an approach that works quite well.
Okay. Thank you very much. And another question, do you have like since you are in the domain, is it important to work with scientists and researchers who work on traditional techniques of the problems that you consider when you start working on new problem to apply this approach?
Yeah, I mean, there has to be some level of understanding of what's the state of the art in this in this problem. But again, like what I like in this domain is that I'm assuming that most people that are in this in the audience are maybe coming from computer science, for example, and so on. The beauty of this is that you can really apply it to different computer science problems, and as a computer scientist, it's easier for you to understand, you know, like what I discussed today than it is to understand, I don't know, like other domains like biology and so on, right? So most of the domains I talked about today, we were not expert in any way on that, on these, right? So we just you know, like talked to some people in this area, read a little bit, and then we were up to speed essentially, right? As opposed to, you know, like if we were to do something in biology, as myself, for example, I have very limited knowledge of biology. That would need, you know, like years in order to actually yeah, be able to make discoveries in that space and so on.
Okay. And, and also we would like to ask, so the World Intellectual Property Organization, WIPO, has defined four types of uses of AI in the invention context, and mainly one of them is that AI generated invention. One of these types is AI generated inventions that are made autonomously by AI without any human input. And do you have any thoughts on this category? And do you see that your work, like algorithm discovery, can fall into this type with time?
So without any human input, that's interesting. I think one needs to define what does human input mean. So for example, you know, the kind of it's still, you know, like at the end of the day, there is still some human input. For example, you know, like as I was saying, if you give it a blank sheet of paper, it's not going to be able to essentially, you know, like uh, make new discoveries. So you need to set it up in a way that has some level of, you know, like the skeleton, for example, that has some level of context about what problem we're dealing with. So there is some level of human input. Now, having said that, I actually believe that and related also to the previous question, is that if we feed in too much human input to the problem, then we will actually not get any new discovery. So say, for example, I was fine-tuning the LLM on existing heuristics to solve my problem. Then what I'll be getting at the end is something that is very, very similar to what I trained it on or what I fine-tuned it on, right? So it's really important to kind of achieve a you know, like a good compromise between not giving it anything and giving it enough so that it's essentially able to do something that is of interest, right? So I think, yeah, if you want a new result, you really need to find the right balance here.
Okay. So maybe in the continuation of the same question, so you talked about giving earlier, you talked about giving like a skeleton of a greedy algorithm to the
Yeah,
LLM
yeah,
to learn on. But if if we can imagine that these techniques can be used to solve very difficult problems that we do not know how to solve, for
yeah,
example, maybe solving millennia questions like is P equal to NP,
yeah,
discovering polynomial algorithms for the NP-hard problems,
yeah.
this can be done with a classical skeleton that we already know. Do you think that AI can be used also to discover algorithms in this sense?
Yes, but that's more on the theoretical side. So after you get an algorithm, you need to essentially like prove that it runs in polynomial time and so on, right? So there is a verification part that is needed.
Mhm.
But you'd actually be surprised at how much I mean a lot of work has been done in this area. So there are some good ideas, right? So putting those good ideas in the prompt can be helpful, right? So even if you don't kind of force the LLM to use those ideas, putting them in the prompt can really be helpful so that it builds on top of it, on top of these, right? So I'm not a fan of essentially starting everything from zero, because starting everything from zero is very essentially data greed, it involves a lot of reinventing the wheel, right? And it requires a lot of data, right? So if you have prior knowledge about the problem, put it either as a skeleton, as I described, or as in the prompt, so that at least it sees what has been before, right? But so I think the whole success of this approach is to let the LLM or constrain the LLM to do the things that we as humans are not able to do, right? And let it do what it, and let it kind of fly on that. Don't give it instructions too much, but do a compartment of okay, what's known is this and what's not known is this. You do this, but I know what the structure is, or I know what's the existing results and so on. Yeah.
Mm-hmm.
So at the end of the day, it is some sort of a human machine collaboration. So I wouldn't say it's kind of completely from zero human. Yeah.
Yeah, of course, of course. Well, thank you very much. And if you can just take 1 or 2 minutes to give a last word or last thought to the community of MoroccoAI. So you have young researchers, engineers, a lot of people interested in AI and in computer science in general. Do you have a word for them and advice for this community?
Yeah, I assume that most people that are joining here are Moroccan. So I'm someone who went a lot to Morocco, and someone who's really fond of Morocco. So I've been to UMCSP and so on. And there is so much opportunities to do, so many AI opportunities there that I'm really fascinated. So one thing that is really, I think, important when I get asked this question is, do not try to kind of copy the kind of research, or do not try to just do the or build incrementally on existing research, right? Try to think about new directions of research, and things that make the research you do quite different from the existing ones, right? So try to really look at things from a new angle, as opposed to just building small increments on top. This is, I think, really fundamental. And one way of doing this is asking, okay, these big labs, which are really pioneering this kind of research, they are looking into building large LLMs, and they have so much compute, and so they have this advantage. But you guys also have a big advantage. For example, analyzing LLMs, understanding what they're doing. There is so much to do in academia, and even without the increasingly large resources that people at Google, for example, have, these people, they don't have the time to actually think about maybe some analysis of the LLMs and so on. So what my recommendation would be is to essentially ignore a lot of the noise. So there is a lot of noise in AI, right? So and try to think about what would be actually an impactful thing to work on, and be committed, and be a big believer in these ideas, and go forward, even if there are some hurdles in the beginning. We had a lot of hurdles also at the beginning and so on. So yeah, just my 2 cents.
Well, thank you very much. That was very, very cheerful and very insightful also. Well, we thank you again for accepting to be a speaker in our conference. It was a great honor to have you, and the talk was very, very interesting. So thank you very much on behalf of MoroccoAI organizers, and on behalf of MoroccoAI community. Thank you very much.
Thank you very much, Ziad, and everyone. Bye.